1, leading to a net gain of -1 in each case, or a loss of 1 if you prefer to say it that way. If the die lands on a 6, though, the payout is 7, so the net gain for that case is 6. On a fair die, these 6 possible results are all equally likely, so we can combine the equations together and divide everything by 6 to get the average payout, cost, and net gain. One way to read this equation is to say you have a 1 in 6 chance to win the benefit of 7 coins, and it costs 1 coin to play, so you expect to win 1/6 of the coin per time you play.
I think this is another math equation.
Yeah. It's too difficult that though. You know? I'm looking at the numbers, Ada. Looking at the difficult watch it.
Can I just learn it from a YouTube video?
The coins only come in whole numbers, but the average is a fraction. An average predicted result like this has a special name. It's called an expected value. And since the expected value here is positive, the blob should gain money over time by continuing to play. It looks like the blob is actually doing way better than 1/6 of a coin.
6.
So basically, this is the thing he's doing. He's making a simulation.
Why the answer is? What is the answer?
So he's doing the simulation of basically just the gain of the. So basically, you roll a dice. If you get anything under 6, you don't get anything. But if you get a 6, you get 7 coins and cost 1 coin
Please.
to play the game.
Okay.
So that's what the simulation he's doing.
That's good for the blob, but not so good for our prediction. It's only been a few rolls though, so maybe the blob is just getting lucky. If our prediction is good, it should start to look more accurate with a larger number of rolls. So let's enlist some more blobs to see if that happens.
Pero sa isa kasi hayag ka kung nawungpod diri dili. Pangit siya front cam. Pero sa isa nito.
Well, it's starting to get pretty close. It can sometimes take surprisingly long for
Wala lang, video lang ko sa akong cell kaya nakuddan ako video pang kanino.
We can use variables to write this out in a way that will apply to a broad.
Alright.
Ay, tama di ang bulan.
Alright. So now we have another equation. BP minus C equals EV. That's the second equation
Set of situations.
that I have
The
now.
benefit of winning times the probability
Sili
of winning
dalahan.
minus the cost to play is the expected value of a gambling game. If the expected value is positive, it's usually a good idea to gamble.
Hala ka, uy.
And when the expected value is negative, like in every single casino game, for example, you should expect to lose money. You might notice that this looks basically the same as Hamilton's rule already.
And I have multiple equations.
So let's try applying it to a biology simulation to see how it works. We'll start with the same basic structure from the video on green beard altruism. Each day, blobs will go out to the forest to eat some fruit. Some of the trees have predators in them, though, and if the blobs are unlucky enough to visit a tree with a predator in it, they'll get eaten. But if they don't get eaten, they'll head to one of the homes and reproduce, creating a puddle of 3 new identical blobs in their place. And yes, A group of blob siblings is officially called a puddle. And after the blobs reproduce, the cycle repeats. Also, when it's time to go home, there might not be enough homes to go around, in which case some randomly determined blobs won't get to go home and reproduce. In case you've seen that green beard video, I want to highlight the key difference here. This time, the siblings always stick together in their puddle when they go out to a tree. There's no altruism yet, but let's make this a bit bigger and let it run for a while to understand how the simulation works in this baseline case. Alright, it turns out that the blobs thrive in this environment, and the limiting factor ends up being the supply of houses. The blobs should really figure out a way to build more housing, but...
Lolita, I'm gonna make what is it called again? A graph on who likes more colors.
Okay.
So first, like that, and that. So we're doing in ones now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. It ends at 30. 30. Finally, another use of the eraser of this thing.
Hello. Lista the book na naman.
1, 2, 3. Let's just start out with 3 colors.
Sige.
So green, red, and blue. We're gonna do 3 colors.
Dili, nag-message ko daan sa imo. Wala ni mo gitanaw.
Green. Yeah, that looks wrong.
Pagtawag niya sa imuha, nagagunit na ko sa iyang kamot.
The line graph is done. So my favorite color is blue, meaning 1 point for blue. And what is your favorite color, Narita?
Green.
Okay, so 1 point for green. So now we have a simple bar graph. Now only one doesn't have a point.
Okay, now let's add the ability to be altruistic. Again, this will be pretty similar to what we saw in the green beard video. When the blobs go to a tree with a predator in it, one of them will notice the predator, and it'll have two options for how to react. The first option is to just run away, leaving the other blobs to die. We'll call this the cowardly behavior. The second option will be to make a bunch of noise to warn the other blobs, but in the process attract the predator's attention and end up getting eaten. Because these blobs are sacrificing themselves to help others, we'll call this the altruistic behavior. The behavior will be controlled by a gene, which has two versions or alleles. The cowardly allele will be blue, and the altruism allele will be orange. The blobs can't actually see the genes, but we're going to use these colors to graph the frequency of each allele over time. I mention this in basically every video, but I can't say enough how in real life the cause of behaviors is very complex. It's only partly genetic, and the genetic part itself is a lot more complicated than this model we're using here, where just one gene controls this one kind of behavior. We're just using a simple model to explore one small piece of the very large picture of behavior. But with that said, let's run this simulation. We'll start with equal numbers of each allele. Before we hit go, though, what do you think will happen? Will one allele take over?
Okay. I get to do the line graph now. More tests on it. We got the line graph here. Look at it. It goes all the way up to 30. We have green, red, and blue.
And then,
which are, I think, the main colors that can, if you mix together, gives you all of the other colors. Now, I will go and rest my left leg because it hurts.
makalasa dakil.
It's okay. My left leg hurts. I don't know why.
Bye.